We are going to do a quick recap of what it means for a function to be onto, and then we'll do a couple of examples of onto functions and how to prove that they are onto or surjective. Diagram, it's actually very easy to spot when a function is onto and when it is not onto. So if we have a function f from a set A to a set B, it will be onto if all of the elements in B are being mapped to from elements in A. So the first figure that you see on your left, you will see that every element in B, the 1, the 2, and the 3, are associated with elements from A. If a function is not onto, like the one on the right, you will see that there are elements in B that are almost isolated from the relation. They are not being used, like the element 3 in this case. How do we spot if a function is onto or not onto? Well, if it is onto, it means the image of the domain, or f at A, f of A, will be equal to the codomain, the entire codomain. Basically what it means is the range will be equal to the codomain. If a function is not onto, it will mean the range of the function is a proper subset of the codomain. So here the range for the figure on the left, the range for the function is the entire set B. That's what it means to be onto. In the second example on the right, you will see that the range only consists of elements 1 and 2 from B, but not 3. So here the range is a smaller set and is contained in the codomain, but not equal to the codomain. Take a look at the formal definition of an onto function. So if we have some function from a set A to B, we say it is onto if f of A is equal to B, meaning the range of f is equal to the codomain of f. What does this mean for us if we would like to prove that a function is indeed onto? Well, it means that if we pick any random element in the codomain, so if for any b in B, we are able to find the existence of an element in the domain. So we are able to show there will always exist an A in the set A, such that A gets mapped to B, or f of A is equal to B, then our function is onto. So basically the idea is if we have a domain and a codomain, and we pick any random element from the codomain, we should be able to show that we will always be able to find an element in the domain A that gets mapped to B. For our first example, we have a function from R to R, and it's defined by f of x is equal to x squared minus 4x. This is a parabola. It is upward facing. It has been translated horizontally and vertically. But the question is this function onto or not? Now, what's important is we need to know about the function, but we also need to know about the codomain. So for an onto function, what we are going to check for is that the range of the function should be equal to the codomain. In this case, the codomain is defined to be R. Now, because we have a parabola, the range is immediately restricted, right? We've actually taken a look in the previous videos at this parabola quite a bit. The x-intercepts, if we make f of x equal to 0, are at 0 and 4. And it's upward facing, so it would look something like this. Axis of symmetry would be right in the middle at x is equal to 2. And if we substitute x is equal to 2, we get f of x is negative 4. So the range of this particular function is going to be from negative 4 included up towards infinity. And this is definitely not equal to all of the real numbers. It's a subset of the real numbers. So this particular function is not going to be onto. Another way of seeing it is, remember we said A function will be onto if we pick any random element in the codomain, and we will always be able to find an element in the domain that maps to it. So if we pick an element that lies outside of the range, so if we say, for instance, let y be equal to -5, and this is an element in R, specifically in the codomain. Can we find an x in the domain, so a real number, where f of x is actually equal to 5? Is this possible? Let's see if we assume this is the case. So f at x is equal to -5. Will this cause a problem? Well, f of x is equal to x squared minus 4x. All right. So we start with y is equal to -5. This means f of x is equal to -5. So this means for some x, we have x squared minus 4x equal to -5. Let's take a look. If we take the -5 over, we get this quadratic equation. X squared minus 4x plus 5 is equal to 0. We would actually like to show that no such x will ever be found. So how would we show something like that? Well, this is also quadratic, so it also refers to some parabola. If we can show that there are no roots or no solutions to this equation, then we are done. It means we will never be able to find an x that satisfies this. How can we show that we will not be able to find such an x? Well, we can take a look at delta, right? Delta is b squared minus 4ac. It gives us information about the roots. This coefficient of x squared is our a. Coefficient of the middle term is our b. And the third term, the constant, is our c. So delta will be b squared, which is 1, minus 4. No, b squared is not 1. What am I doing? B squared, b is -4, so this will be -4 squared, minus 4 times a, which is 1, times c, which is 5. So we get delta is 16 minus 20, and this is definitely negative. And we know if delta is negative, it means there are no solutions to this equation. So no solutions. This means we cannot find an x in the domain that maps to -5. So this function is definitely not onto. Here's another example of a function from R to R, and it's defined by f of x is equal to 2x plus 3. Again, keep in mind, what are we working with? This is a straight line. It's not horizontal, so the range is the whole of R, and the codomain is defined to be R. So this definitely looks like it is an onto function. Let's try to prove it using the definition. So we are going to start again by picking any random element from the codomain. So let's pick a B from R, in this case the codomain. What we are going to try and show is that there exists an A in the domain that gets mapped to B. So we are going to say, we can here choose A to be some expression, some element, specifically from the domain. And we have to show it's in the domain. And then we are going to show that f of A eventually is equal to B. So these are the three parts of our proofs. I'm going to name or number them like this. The first part is picking a random element from the codomain. Second one is specifying that there will exist an element in the domain, and then checking that that element actually maps to B. How do we choose our A? Now, this is something that you can do rough work for yourself. I'm going to do it here at the top. We are picking something in the codomain. We are trying to show that we will be able to find an X. So what we are actually doing is we are going to try and reverse our steps. So we are assuming that B is equal to some 2A plus 3. We want to know what A will actually look like. If this were to be the case, we still have to test if it is. Okay, if we try to solve this for A, we can take this, the 3 over to the left-hand side. It becomes B minus 3 is equal to 2A. And this is true if and only if A is equal to B minus 3 over 2. Okay, let's choose this to be our A. We have B minus 3 over 2. It almost feels like we are cheating, but we really aren't. We are just retracing our steps, working backwards to see if we can find an A. The most important thing is we need to check that this A that we have found is part of the domain. If it's not possibly part of the domain, then we cannot definitively prove that this function will be onto. So let's just take a look at the expression for A. We said A is B minus 3 over 2. So we would simply have, if B is a real number, B minus 3 would still be real, and we are dividing by 2. So that is still ultimately a real number. We have to confirm this. This choice of A is indeed in R, and R is our domain. Now, if at A, just for confirmation, this is f, or this is equal to, f of x is 2x plus 3. So f at A will be 2 times A plus 3. We substitute our A. So this is 2 times B minus 3 over 2 plus 3. The 2's will cancel. Then we have B minus 3 plus 3. We end up with B. So here we can make our conclusion. Therefore, F is onto. A lot of students every year will tell me that we will be able to do this process for any type of function. So if we always reverse it, we will always be able to find an A. Because we reversed it like that, if we plug A into the function, it will always take us back to B. So we can use this method to prove any function is onto, even if it isn't. So with something like this, we need to actually be very careful, because it is true, if we do this part, let me get my highlighter here. If we do this reversing rough work part where we assume B is equal to 2A plus 3, we would always be able to solve for A, and if we plug that back into the function, it should take us back to B. The main thing is what we end up with here for A. The main thing is that we need to check that this is actually part of the domain. So for functions that are not onto, yes, we can follow the same approach blindly and mistakenly prove or try to prove that a function is onto. But what would happen in that case is that this expression that we find for A would not necessarily be part of the domain of the function. That's the difference between actually being able to prove the onto or not. Here is another example, and this one's actually quite interesting. You might not like this one very much because it doesn't look clearly like an obvious function that we can quickly recognize, like a parabola or a straight line. Um, and we have some restrictions. It's not just a function from R to R. In this case, we have a function from R without the number 0 to all of the real numbers. So the domain is slightly restricted. And we can see why, right? If we look at the function f of x is x plus 1 over x, the domain does not allow x to be 0, because then we would be dividing by 0. But how on earth would we determine whether this is a onto or an onto function or not if we don't know what the graph looks like? Well, we have to do a little bit of inspection here. Remember, if it is onto and we have some element in the codomain, any element in the codomain, we should be able to find an element in the domain that maps to it, right? So that's what we're going to do. I'm just going to start here, just not with a formal proof, just to show you how we would tackle something like this if we didn't know what was going on. So what I'm going to start with is I'm going to say let B be an element of R. In this case, this refers to the codomain. And I'm going to assume there does exist an element in the domain, an A in R, such that f of A is equal to B. So if this is the case, then it means that B is going to be equal to A plus 1 over A. Sorry, and I'm just going to fix this. A is from the domain, so it is R without 0. Now, because A is not equal to 0, we are allowed to cross multiply here. So this is actually B over 1 equal to A plus 1 over A. So we are allowed to cross multiply because A is not equal to 0. We can say that this is equivalent to AB equal to this product, which is A plus 1. And now let's see if we can just, what we really want to try and see is if there are any problems. If we go this route, if we assume that it is onto, do we end up with an issue or not? So we started with B being equal to something. So what I'm trying to do here is I'm trying to solve the equation for A. Can we describe what the A looks like that gets mapped to B? So what I'm going to do here is take all the terms with A over to the left-hand side. So we get AB minus A and everything else over to the right-hand side. And then we can factorize out the common A here. What will be left is B minus 1. This is equal to 1. Now, can we solve this equation for A? How would we do it? Well, we would divide by B minus 1 on both sides of the equation. Right. So we are allowed to say this. A is equal to 1 over B minus 1 as long as B minus 1 is not equal to 0. So as long as B is not equal to 1, we are able to solve this equation for A and get something that will ultimately map to B. What is the problem? We said here, right in the start with our assumption, we assume that B is any element of R, including 1. But now we've concluded that B is not even allowed to be 1. So we have a bit of a contradiction here. For B is equal to 1, we actually run into a problem. So this is going to be our counterexample that we will use to show that this function is not onto. Right. So this was just our a few calculations, a bit of rough work that we did. But what we are going to do now is we are going to start with this. We are going to start with let f of x be equal to 1. What is this going to cause? Well, it means then that x plus 1 over x is equal to 1. And this is true, again, if we cross multiply or multiply by x on both sides. This gives us x plus 1 is equal to x. And we're allowed to do this because x is not equal to 0. But what happens now? We have x on both sides of the equation, so that's going to cancel, and we end up with 1 is equal to 0, which is definitely a big contradiction. And so this means the assumption that we made, that f of x could be equal to or reach a value of 1, was wrong. Meaning there are elements in the codomain here, specifically in this case 1, where nothing is actually being mapped to that 1. So this is definitely not an onto function. It means actually, it means the range of f is not equal to the codomain, which is R. The range of f is going to be smaller than R. Just to convince you, or just to give you the fuller picture, what is this function actually? We have x plus 1 over x. What does it look like? Well, if we just break up the function, we get x plus 1 over x. If we take that fraction and we just split it into 2, and because x is not 0, we can cancel x over x, which gives us 1 plus 1 over x. The 1 over x is a hyperbola. The plus 1 means it's been shifted 1 unit upwards. So the graph, if we had to draw the graph, the standard hyperbola 1 over x has an asymptote at y is equal to 0. So if we move it 1 unit upwards, asymptote is going to be at y is equal to 1. Can you see the problem? Y is equal to 1, f of x is equal to 1. That's exactly why. So here we have our shifted hyperbola. All right. What is the range of this hyperbola? Well, it's all real values except where the asymptote is. So except at 1. And this is the reason why it's not onto. The codomain allows for all y values. The range, the actual range of this function, doesn't allow for y is equal to 1.